Hello guys, my name is Shaun, and today in this video we are going to make custom shellcode. So in the previous videos we have discussed what a shellcode is and how it can be used for developing malwares. For example, I have coded a shellcode runner in C. So we will also use that code in today's tutorial to demonstrate our shellcode is working or not. But today we will make custom shellcode in assembly, because if we make shellcode using something like let me zoom it in a safe venom. If we use a Metasploit standalone payload generator like this as a venom, so what it does is that it is detected by Windows Defender very easily. So in a lot of actual pen tests, uh, the adversaries may utilize custom shellcodes. So we are gonna learn the most basics of custom shellcode. So we are in a directory. This is the directory, and let me zoom. Can I zoom? I think more. Yes, it is enough. So okay, I have a hexdeal.py and a shellcode extract.py. So both of these are scripts to this hexdeal.py. This is a framework coded by me. So it just deals with hexadecimal characters. Then it can convert normal decimal to decimal, not decimal. It can convert string to hex, then hex to string. It can reverse the string and can do a lot of stuff. So like python 3 hexdeal.py, we want help. So it does hex on hex edit. Then it has ref, reverse to input, cut the output as specified, comment, it comments, then comment symbol. So that is this is a default symbol of assembly comments. Then there is ref bytes, so no prefix, and everything is there. So let's just give you an example, calc.exe, but before that we will have to specify hex calc.exe, and then let me say comment. So this is the output and this is the comment. So this is the hexadecimal representation of calc.exe. So if I copy that, and because I have pawn tools installed, I have unhex, but I will have to remove the 0x, and I have got calc.exe. So you can see that it works perfectly. Then there's comment, then there's cut. We have to, if we have to break it, then you can ref. So exe.clack, this is the output. So there is a lot of things you can do with this program. So I will make it available in my GitHub. And then there's of course the shellcode extract.py. This is actually a GitHub project, not owned by me. It is another person's project, which let me open it in Sublime Text. So you can see that what it does is, when we have a object file, that is the compiled output of a assembly file. So that is an assembled output actually, not compiled. So when we dump the contents using objdump, then pipe that output to this program, so it gets that output and does all of its thing and finishes the shellcode. That is what it does. So well, okay, so let's just start with the to-do.c. So here what we will do is to demonstrate how our shellcode is gonna work, and I have to zoom it. Include windows.h, that is the wrapper for call the Win32 API functions, make our main function, and we will use WinExec. So what WinExec does is that let me yes, so what I was saying, so what WinExec does is that it calls this function, okay, and SW normal is refers to just the window size and all the thing. So if we go to WinExec msdn, so that is the Microsoft documentation for WinExec. It says it has the first argument is LPCMB line, which is of course LPC string. That means long pointer C string. That it is simply a string, and then there is the unsigned int UCMD show. So that is actually an integer. So the LPCMB line means the command, the exe you want to run. That for our case, we want to run calc.exe, which we can directly reference because it is in the path environment variable. So we don't have to mention the absolute path. We can use simply the calc.exe. Then there is of course the SW show normal parameters. So SW normal or SW show normal, whatever you want to use, both of they have the value is 1, so activates and displays a window, so you can study on that. So for now, let's just save the program, compile it using gcc, that's o to do, then to-do.c, and we will have the to-do.exe here. So if I run to-do.exe, the calculator is portable, so the program works perfectly. So let's just delete all the to-do things because we don't need them. So it's just a demonstration how the shellcode is going to work. Okay, so let's just open something like shellcode.asm. ASM stands for assembly. Okay, so I have the nasm assembly x64 downloaded here, you can see. So if you want to download it in Sublime Text, you can do it manually using the package manager. It is Ctrl+Shift+P and then install. So package control, you can install package. So simply, okay, let's just go on with it. Let's make a comment, pop calc.exe. So okay, so this program opens calculator, and then let's start with the most basic thing, that is the make the text section which contains the executable code. So okay, we have made the text section perfectly. Then there's the global underscore start, which start will be the function from which the execution will start. So let's make the function, and let's do the comment here. So let's just talk what have we done. For this video, I am expecting that you all know the basics of assembly language. So I don't want to explain all of this, why I have written this now. So we will just go with the simple code. So zor rax, that means actually when you zor rax with rax itself, rax is nulled out, so it is equivalent to the code move rax 0, that means move 0 into rax. So it is equivalent to that, but because it looks kind of more cool, so we use that very simply. So let's give the comment 0 out rx. So okay, so actually why we are doing this, because in the next argument we are going to push rx. That means push the value of rx, that is the backslash 0, which is the null, terminator. So, and after that we are going to push the calc.exe string. So for that, let me just do python 3 hexdeal.py hex calc.exe dash cut for, because that is optional. It just cuts all of the things in equal halves. So it is 4 bytes, like 63, then 61, then 60, then 63, then there's also this is the other half. So then we want comment, so that it comments out this thing out. And the most important thing that we want to do is use dash rev. So what dash rev does is actually reverses the string, not that it doesn't reverse the bytes but the order of the bytes. It is very important because when we push things in stack, it is stored in reverse order. So that is why we have to use this. And let's just copy that, paste that, push that. So we are actually pushing something like this: 0 exe dot calc, and the 0 is actually the backslash 0, that means the null terminator. So we are pushing the string like this, push into the stack. Okay, so we want to move the address of the pointer to this string, which is stored currently in RSP, or the stack pointer. So we want to move that thing in RCX, and I will explain that. So not RX, that is RSP. So by default, when I use RSP, so it just what move does is that it moves the address of RSP, the pointed thing, into RCX. It doesn't actually what it does, it doesn't actually dereferences. So if I do something like this, so it will dereference. So what it actually means is that this thing here is moved into RCX. We don't want that. We want the address which points to this string in the stack. Okay, so that is why we are using move. Equivalently, we can also use LEA, that is load effective address. We specify RCX and then specify RSP like this, but I prefer to go with move, so we will just go with move. And if you know what RSP is the stack pointer which denotes, or which points the top of the stack. Okay, so it is the stack pointer, and then this RCX. So there is an article, it is a very good article. So what it says, that register the first 64-bit Windows uses 4 registers to pass parameters to functions. Any more than 4 and the stack comes into play. So the registers are in order: RCX, RDX, R8, R9. It means that given a function whose signature is similar to this, int add A, B, C, D, move RCX A, RDX B, R8 C, R9 D. So that means RCX holds the first argument, RDX holds the second argument, R8 holds the third, R9 holds the fourth. Okay, and then there's concept of shadow space, which we will also get into a little bit later. So RCX holds the string as we have noted in the WinExec function. So that is the LPCMD line which holds the string. So let's just comment that LPCMD line. So LPCMD line. Okay, so then we have to move rdx into rdx, but we need to move 0x1, and 0x1 actually needs decimal one. So that is I think pretty basic, and it is the what it is, it's the ucmd show. Okay, and it means actually sw normal or show normal, whatever you want to call it. And then there's a concept of shadow stack. So what shadow stack it is, you can study it. So you can study it in deep, but I will explain it in brief. So this in Windows, there is the Windows NT kernel wants the stack to be aligned in a particular way. So if the stack is not aligned properly, the program will not execute properly. So that is why we have to subtract rs from rsp some bytes sometimes. So how it is calculated? So that is calculated this way. So first of all, we are pushing, here is 4 bytes, here is 4 bytes, and here is this thing. So let me open Python. So the 4 plus 4 plus 1, so that is 9. Okay, so what we have to do is subtract 0x20 from rsp. I think my brain is not braining right now. I don't understand why I am doing that. So maybe I will also have to study it a bit. So it's a 64-bit API specifies that every single function allocates 32 bytes of stack space for register spill. This is commonly refers to as shadow space. So okay, so it means that okay, so the stack must also always be 16 by aligned, which can be considered because on entry to a function, that last entry stack is the return address that it is defined already 8 bytes. For a function to allocate 32 bytes of status state and keep the stack alive, must allocate 40 bytes, 40 plus 80 equal 40, which is a multiple of 16. A simple example would be sub rx rsp is return address bytes on stack. So call the function. So okay. So we would have to subtract 0x28 by default if we don't have pushed these things, because now we have pushed this. So there is a 4 here, and I think the null is not counted. So that is why when the thing is when 28 minus 8, it is 20. So and 0x20 actually means 32 in decimal. So that actually aligns the shadow space. So I think that will be enough for me right now. Of course, I will have to study it a lot more. Now we will have to get the address of the function, that is the WinExec. Then we could call it. So, okay. So how should we get the address of the function? We can make a program for that. So let's make a program, findaddr.c. So let me just mention that all these things have been previously done by me, but because I am a very beginner in all these things, so my own understanding is a bit less than what you'd expect. So maybe the teaching which I am providing right now would be not as satisfactory as you would expect from the experts in this field, but I am providing what I can and the best I can. So let's just go with that note. So let's just include stdio.h. Let's just include windows.h and make the main function. Now we will have to make h module kernel 32 addr, and then we have to make far proc func addr. So if you ask me from where I am getting this h module and far proc, so I will explain that in a bit moment, but just know this: these two are like type descriptors for this variables. So these type descriptors come from windows.h. So I think that is pretty obvious for you if you have done using windows.h functions. So I will get to it in a moment from where I am getting this h module and far proc. So but before that, we have to get the address of kernel32.dll. For that, we just do kernel32.dll ttr equals get, then there is get, it was not proc handle, it was get module handle most probably. So then there will be kernel32.dll. so let's just run it and see if it is working. Not gcc kernel gcc find addr.exe. So it I think it works. I have to print it actually. %p kernel to edit. Okay, I think it is working. So if you ask from where I am getting h module, let's just make it something like int. Super simple. So when I run gcc, it will give me an error that assignment to int from h module. So from there I have used h module. Similarly, that is so for far proc. Okay, so that is func addr will be get proc address of WinExec. That is the function we want. So printf WinExec address %0x %p\n func addr, and let's just do that with the kernel32 as well. Kernel32 addr. So I think that should run. Okay. So the first argument is connected to a DDR handle. So I think that should work now. Okay, I think it is working. So I have to give a disclaimer that this is the address of WinExec now currently in Windows. So if you reboot this machine, it will change. So hard coding the address in the assembly file or shellcode is a very bad practice, so you should not do that. But because we are the beginners, it is the first video of learning custom shellcode, so we will hard code the address into the shellcode. So for that, let's just move into something like rax, the address, then just call rax, and the program should work. For that, just do nasm -f win64. Note this is a 64-bit assembly for Windows. So then I think the syntax was like shellcode.asm -o shellcode.o for object file. So if I do the, I think it is there. So if I do like clear screen, and then there is ld, that is the so if you ask from where I am getting this file, so I am getting these commands because I have installed the mingw w64 from winlibs and put it into path. So from there I am getting these things. Okay, so ld shellcode.o -o shellcode. So if I do the, I have shellcode, but I have to move it to an exe to run shellcode.exe, and it pops the calculator. That means our assembly has been perfect. And if we open the shellcode extractor again, it will say that objdump-d example.o. So it will say that objdump-example.o, not example.exe. So we have to do objdump on the object file, not the exe. So let's just do that. Not example, it is shellcode.o and -d. So I think that is perfect. Then we have to do is python 3 shellcode extract.py, and it has printed the shellcode with the length is 38. Okay, so what we need to do is to create the shellcode runner. For that, we just create x64.c. We include windows.h. We make unsigned char buff equals to this string right over here, slap that in, semicolon at the end, create the main function, create the return 0, then first function handle mem equals virtual alloc 0 size of buff mem commit mem reserve page execute read write. I think that was the syntax. So virtual alloc mstr. So virtual alloc mstr provides us with the page execute read write. Copy that, paste that, semicolon. Then there's mem cpy, that is mem copy, and that the syntax is the destination, that is mem, then there's the source, then there's the size of source, that is the syntax, and then we have to call that. So for that, I think I am doing it correct. Yeah, I think I have memorized the syntax. This is the exec.c dash exec. Exec, and calculator pops out. So we have created the custom shellcode, assembled it, and extracted the shellcode from it using objdump, and then we have successfully run it using the shellcode runner we have created in the previous video. So that concludes the part. But if I want to say that the actual red team engagements and actual malwares use much more complex custom shellcodes than this, so I will teach some of that later, as I myself will learn all of that, and I am very excited to learn all of that. So with that note, I am concluding this video. So this was Cyan from Smiths, and we will meet in the next video. Till then, take care and bye bye.